worries.
Okay, now it started. Yeah.
Yeah.
So,
So I'll just summarize the last slide, but basically using GNN plus LLM, we were able to double the accuracy of standard LLM based graph rag solutions. And yeah, this is pretty impressive. We wrote a blog about it and the work is open sourced on GitHub. So this is a slide from a recent talk given by one of the founding fathers of modern AI, Jan LeCun. See the QR code in the corner for the full slide deck that this comes from. The key point of LeCun's slide that I want to highlight is the part mentioning that the probability of being correct is a diverging function with respect to the number of tokens n. For the equation in LeCun's slides, E represents the error for next token prediction. Even if the error for next token prediction is near zero, the chance of our entire sequence being wrong becomes high very quickly. Because of this, there is an obvious need for some fundamentally new ideas besides brute force scaling of LLMs. This slide has been adopted from a 2023 talk given by the creator of PyG, Matthias Fay. He defines GNNs as models that update node representations by repeatedly transforming and aggregating representations of direct neighbors. The diagrams here explain this quite well, and I'll walk through each. The top is the most basic example. We have a single layer of a GNN, which computes the embeddings of any single node. In this case, let's look at node 1, as a function of the embeddings of its direct one-hop neighbors. One can think of convolutional neural networks and transformers as subclasses of GNNs, much the way that triangles and quadrilaterals can be thought of as subclasses of polygons. The diagram for the convnet shows how a convnet across pixels is the same as a GNN over a graph of pixel nodes connected to their direct neighbors in the image. For the transformer diagram, you can see that the transformer attention layer is essentially a GNN over a fully connected graph of the tokens. In general, an n-layer GNN learns to predict over n hops of information in the graph, which makes them excellent candidates for enabling multi-hop reasoning in AI systems. This is essential since multi-hop reasoning is a key aspect of human intelligence. An example of my two-hop neighborhood is me, my friends, and all of their friends. Our research finds that GNNs can improve LLM accuracy. We believe this to be possible since GNN embeddings on graph data can provide a semi-orthogonal source of information. LLMs tend to be much larger than GNNs. A transformer layer is essentially a GNN on a fully connected graph between tokens. However, the transformer uses parameters to learn the importance of each connection, while GNNs do not need to parameterize how entities are connected, since the graph data provides this information. As a consequence, adding in GNNs has almost no effect on the total number of parameters, as we saw with the Stark Prime example. As an introduction, RAG refers to retrieval-augmented generation. The most basic form of RAG we will refer to as vector RAG. This is where you retrieve the top k most relevant docs based on k nearest neighbors between the query and their embedding vectors. The diagram in the bottom right goes through this basic workflow. This is usually good enough when the answer requires only a single document to be retrieved. Graph RAG is a general term that refers to retrieval methods that retrieve relevant subgraphs for the query. This is generally supposed to shine when the answer requires multiple documents with related entities. Here, we have a diagram of a made-up NVIDIA org chart. The question is, who is the shared coworker between Bob Joe and Ronald Coleman? At first glance, the answer may not be perfectly obvious, even to a human. But thanks to the highlighting of the key nodes and edges, the answer becomes obvious. Arno source finger. Using PyG, a GNN plus LLM gets the answer right, while the corresponding LLM fine-tuned the same way fails to answer correctly, even though both models were fine-tuned on the same general knowledge toy dataset. The pure LLM approach I described is generally similar to most graph RAG workflows today, such as the one popularized by Microsoft. In school, students reading English would read left to right, just like an LLM. But exceptional students either mentally or physically highlight key ideas and form complex relations between them in their brain. I like to think of GNNs and graphs playing this role for the LLM in a GNN plus LLM system. On June 12, 2017, the famous Attention is All You Need paper was added to arXiv. Just 5 days earlier, Yuri Leskovic's lab published the GraphStage GNN, which is one of the most well-known GNNs. Since 2017, the AI industry has poured a majority of its effort into LLMs, establishing a strong foundation to build on. In parallel, a small but strong PyG community begins to grow in academia. There was also a small group of companies capitalizing on the power of GNNs. Examples include Pinterest, Kumo, and Spotify, to name a few. The goal of this GNN plus LLM work is to combine nearly a decade of parallel AI research. Our goal is to add GNNs to LLMs to advance AI past the current limitations of LLMs. This diagram depicts a general graph-based RAG workflow using GNNs as a prefix to the LLM's inputs. For the sake of time, I will skip over going into the details, but see the QR code in the corner for a previous talk I have given in case you want those details. In short, we retrieve a semantically relevant subgraph based on the query and encode the subgraph with a GNN. Then this is combined with the LLM encoding to produce an output. The GNN must be fine-tuned, so we need gradients to flow through the LLM. For that reason, we use Hugging Face LLMs as opposed to cloud-based API solutions. For the LLM, the best option is to fine-tune it as well as the GNN so that the GNN and LLM can co-learn a new language. If you are very low on compute, you can leave the LLM frozen and the GNN will learn to speak the LLM's language. A third option is to use LoRa as sort of a middle ground. Most RAG datasets only have unstructured text context. As such, there's often an additional task where we must convert unstructured text into a knowledge graph. Our existing PyG framework uses the simple KG format of triples of entity, relation, entity. As mentioned before, LLMs are specialized for handling unstructured text, so they are the ideal model for this task. As our solution to this problem, we have created the text-to-KG class in PyG 2.7. This system consists of a combination of frontier model prompt engineering and some Python filters on top. If you look at the top image, that snippet is the current system prompt for this class, and the snippet at the bottom shows how easy it is to use. In general, we should expect that combining vector and graph RAG is always at least as good or likely better than either alone. GNNs help the LLM decoder to understand graphs, producing better accuracy. This diagram covers the fully combined workflow. As you can see, this is the same diagram from before, but I've added in a block to insert the documents retrieved by any sort of document retrieval method. Since our system is fine-tuned, the LLM should learn to reason over both sources of information. This system is seeing adoption throughout NVIDIA and across many Fortune 500 companies. See example/LLM/text-to-KG_RAG on PyG's GitHub for an end-to-end code exam. In this experiment, we measure the accuracy of a Llama 3.8b generator by using a much smarter 253b reasoning model as an LLM judge. The question-answer pairs for this test were generated synthetically to use multiple chunks of text for each question. We consider the speed of light to be when we feed the generator with the exact context that was used to generate the question-answer pairs. This is what we would consider perfect retrieval. Notice how we are only 1.1% accuracy away from the speed of light. We also perform much better than basic RAG solutions that don't include GNNs. Keep in mind that we did not do any hyperparameter tuning to achieve these results. That is, we use the same set of default hyperparams across the board. So this slide covers a demo made by our PM, Santosh Bhavani. He was able to upload our PyG code to Cursor and have Cursor completely vibe code a graphical interface, showing how easy our framework is to build upon. This is now released as an NVIDIA product. This is great for creating knowledge graphs and then manually reviewing them before using PyG to train a system. I'll come back to this video at the end. So our next major steps for this are integrations into real-world use cases internally and externally. We will also continue to refine the PyG codebase in terms of speed, usability, and accuracy. We will also have our NVIDIA Rapids team optimize the retrieval workflow to enable near unlimited scalability with maximum speed. The idea of using GNN embeddings as a prefix to transformer sequence models is highly general and can be extended to many modalities. The goal of the latest PyG community sprint was to expand GNN plus LLM features to support the sciences like biology and chemistry. There were 4 projects going on to integrate techniques from 3 biology papers and 1 chemistry paper using GNNs and LLMs. The general goal of these projects is to advance medicine and science and integrate general reusable APIs for GNN plus LLM workflows. The sprint is finished now, but you can check out the examples in the example/LLM README on the PyG GitHub or the NVIDIA container. This slide shows just one of the examples called Molecule GPT. This example enables a talk-to-your-molecule experience by combining graph modeling and language modeling to allow the LLM to better understand molecular structure. Check out the links for further details on Molecule GPT. We actually have a very interesting spectrum of graph-like data. On the left side of the spectrum, we have this setting of unstructured data in the form of documents that we must parse into a knowledge graph. This setting is inherently less accurate since we rely on an AI model for this parsing. On the other side of the spectrum, we have data like molecules, hyperlinked document graphs, or relational table data like in RelBench. In this setting, we can assume our graph data is highly accurate. In general, each data source will often cover different knowledge. We also know that most enterprises have multiple of these data sources. Using PyG, you could set up a separate GNN for each type of graph data source, all providing context to a master LLM following similar patterns as discussed before. This technique could also be used to incorporate ontologies created by industry experts. As a final note, today there are 2 kinds of GNNs. The traditional kind are the message passing GNNs. Then there are graph transformers, which are newer. See the QR code for a webinar on the topic I gave with Stanford and Kumo. I'm working with the community to get more graph transformers added to PyG. My goal would be to see how these affect the accuracy of the previously discussed GNN plus LLM systems. In general, most AI practitioners will agree that data is the most important part of a deep learning pipeline, as it is your source of information. For example, even the best model from 100 years in the future can't learn anything if your data is fully random. Graph models, which began as GNNs and grew into graph transformers, will continue to evolve. The key takeaway of this talk should be that structured data can help improve the capabilities of AI, which today learn mostly on unstructured data. This work is built and optimized for the NVIDIA PyG container. Stay tuned to my LinkedIn for new product research and educational updates. As a final note, I want to acknowledge my fellow contributors to this effort and all of the PyG contributors. The PyG community is ever growing and contributions are welcome. Thank you. And yeah, I guess I have a little time, so I can play that video. It's only like 2 minutes.
In this demo, I'll transform biomedical research papers in text format into queryable knowledge graphs using local LLMs. We're using a Llama 3.1 70 billion parameter model served by OLLAMA. Everything stays local: the documents, the LLM, and the detailed knowledge graph throughout the workflow. This large model is key to high-quality extraction, and because it fits entirely within DGX Spark's 128 gigabytes of memory. Let's start by uploading our documents. I'm selecting abstracts from the recent PubMed articles. You can see the documents are now uploaded, and below we're already connected to a graph database that we'll be using shortly. Next, we can configure extraction parameters. Here, we have a prompt that instructs the LLM how to extract relationships from the raw text files. We have additional templates available, and you can configure your own. We'll confirm that we have the right documents and go ahead with extracting the triples. You can see the LLM is processing each document one at a time. Once the files are processed, we can manually edit any entries or triples if needed, correcting or enhancing the extracted knowledge graph. When satisfied, we store all knowledge triples in our local graph database. Let's now visualize our knowledge graph. You can see we have over 3,500 stored triples represented in this graph. I'm going to make this a bit easier by coloring them by cluster. Here, the nodes and relationships are specific and usable, ready for graph rag right at your desk. We hope you check out this demo. You can try it on UDGX Spark by running the playbook linked in the comments.
Yep, so that's all for me. Yeah, I hope you guys enjoyed the talk, and let me know if you have any questions. Otherwise, Jan can take it away.
Cool. Yeah, that's a very interesting project. So I think I do have a few questions.
All right, let me share my screen.
Sure. So
Okay.
do people have questions for the first talk?
Yeah, I have some questions.
Sure, go ahead.
Okay, so thanks for your good talk. I have some two questions about the graph rag. So as far as I know, the graph rag consists of three major stages: the indexing, retrieval, and generation. So my first question is about retrieval. So the traditional, so the question of indexing is how to construct a graph based on the documents. So based on my understanding, there are two ways. The first way is using traditional NLP tools such as I don't know how to pronounce it. It's a SCAPY, SCAPY, to extract the entities and then construct the graphs. And then the second way is use machine learning based, the LLM based tools to construct the graph. So what's the difference between these two techniques? So I can understand that the traditional NLP have many problems because the traditional NLP tools doesn't have capability to tell the context. So, but it seems we can only improve the LLM based approach to improve the graph rag. So can you give me some insights of it? And my second question is about the retrieval stage. So there are also two ways to retrieve the related documents. The first one is heuristical ways. So for example, Microsoft, they also propose graph rag, but they will use top K algorithms to extract related entities, relationships, communities, and text documents. And you said the NVIDIA use GNN, the machine learning based ways to retrieve the documents. So what's the difference between these two methods? So is it worthy to use a machine learning based approach to retrieve the documents? Yeah, that's my question. Thank you.
Yeah, so I can start with the first one. So generally, like, I would say that the like traditional NLP methods, they don't really like scale to like complex text. Generally, they're not used today anymore. I would highly recommend you just using like frontier models. Like that's what our text to KG does. It's basically just querying, the biggest models out there and asking them to format it. I generally think like LLMs are going to keep getting better. And so as long as you have a good prompt, like the kind of text to KG methodology of just trusting the LLM to do it, is more scalable in a sense. I mean, these models have seen everything on the internet by this point, right? And so they're very good at like parsing knowledge. So yeah, I would just say like, the LLM approach is definitely the way to go from here on out. Now that like LLMs have achieved, a certain level of intelligence, so seemingly intelligence, where it's pretty impressive, like what they extract out. It's pretty much what a human, like regular person would do. And they're generally, because it's just an extractive task, there's like less room for hallucination, right? Because they're really just like taking the words from a sentence, pulling some out, and then just adding parentheses and commas. They don't have to do any sort of reasoning or inference kind of task in a sense. And then to clarify for the retrieval step, So that in our pipeline, the GNN is actually used for generation. So you retrieve, and I actually have a slide in a longer deck that that QR code I linked to has all the details, but I can pull it up right now. Just give me a second to share that. So yeah, this is how we do basic retrieval, what we call it. So I think it is similar to what Microsoft is doing. We basically just do k-nearest neighbors between your query and the nodes, and then we do n-hop neighbor sampling. So basically, like, choose friends and friends as friends of those nodes to get like a large subgraph, and then we use something called prize collecting Steiner tree to trim this down further. Prize collecting Steiner tree is based on semantic similarity as well. And it basically like just traverses the graph while trying to maintain like high prize based on semantic similarity. There is research that is on the back burner right now for using GNNs for the retrieval stage. But generally, you would have to fine tune that for your specific data set. And nobody has gotten a foundation model for that yet. Stick around for 2 years and I'm sure it'll come out. But yeah, it's I think for now, like, the basic retrieval is good enough if you have like a strong like you're going to be embedding the text of your queries and your nodes, and so if you're using a strong sentence transformer, it should be relatively good since the phrases are relatively short in your KG. It's not like you're embedding like a long document or something. It's just like short phrases like cats eat dogs, physics is good, things like that, which generally those short phrases are pretty well encoded by even old models like BERT. So yeah, that would be kind of my answer to that.
Okay, thank you for answer.
Yeah.
Cool. Any other questions from the audience for the first talk?
Yeah, I have one. Hi Rishi, I'm Chetan. It's basically on from the slide where you mentioned Lacoon, and he said like LLMs drift. So my question was like, do you like on the slide it showed like the GNN encoder is feeding into the LLM decoder.
Yeah.
So yeah, so do you use a GNN output as a soft prompt for the LLM? And like does this soft prompt as like a hard constraint for the generation, or is it just like a strong suggestion?
So the output of the GNN is basically just being condensed into like a token, so to speak. And so if you leave the LLM frozen, the GNN kind of will learn to like hack the space of the token space and like provide a contextual token that it's like a new letter per se, or a new token that wasn't there, but it informs the LLM of like what's important in the remaining token, in the remaining tokens, especially since like LLMs tend to have a strong bias on the first token. This can have a good impact on that. But generally, the way we suggest is that the GNN and LLM will be fine-tuned together so that they kind of learn to speak their own language in a new embedding space. So yeah, the GNN, like what comes out of the GNN, we're literally just like doing torch cat and putting that before the tokens or like the embedded tokens before we feed that to the LLM decoder.
Right. Okay. Thanks.
Yeah.
Okay, cool. Any other questions? If no more, maybe I have one quick question. So yeah, my question is about, when you say you combine the GNN and LLM together, so is there any similarity between this combination versus the neurosymbolic AI? I think neurosymbolic AI is also trying to do some, rule-based learning at the beginning and then later combine with a conventional AI to distill something out that probably cannot be captured. So foreseeing some shared nature, in these two types?
Yeah, I mean, I'm no expert in neurosymbolic AI by any means, but I do think that generally, from my understanding, neurosymbolic AI is trying to like put our kind of way of thinking about solving algorithms and that kind of stuff into a more codified version of AI. And generally, like every engineering class I was taught, they would teach you the algorithms on graphs, right? Like A-star, Dijkstra's, whatever, MaxFlow. It was all on graphs. So generally, I do think that there should be a strong connect between neurosymbolic AI and graph modeling. I just don't know enough about neurosymbolic AI to go deeper into that. But I definitely think that is an interesting avenue for sure. And I think it would also like help with like explainability of these systems. But yeah, unfortunately, I don't know too much about neurosymbolic AI.
It's fine. It's very, very, broadly, try to gain some, very high level intuition on the potential connections. Yeah, because I mean, some students in my lab also do something related to the neurosymbolic AI. So in this way, I want to see, okay, whether we can, maybe try out the graph neural networks and see, how it further improve. But of course, that's maybe half a year later thing. But I just want to graph something high level. Okay,
I think there's a connection.
Okay, yeah. Any other questions from the audience? If no, probably we should start the next second talk.
Okay, let me share my screen. Okay, can you guys see my screen?
Yes.
Okay, wonderful. Okay, so I'm just going to start with a small introduction. I know Dee introduced me pretty well. And also one thing I want to correct, I say multi-million dollars, not multi-billion dollars. That'd be great if it's multi-billion dollars. But yeah, so my name is Yang. I'm a senior solution architect at NVIDIA. So my title can be a little bit vague sometimes. When I go to a conference in person, when I introduce myself and I say I'm a solution architect, people always ask me, so what's a solution architect? Solution architect basically means that I spend most of my time, helping researchers and companies take the AI ideas and turn them into things that actually work in the real world. So that's actually exactly what I'm going to do today here as well. So I'm going to talk about our blueprints. I'm going to talk about blueprints is because, when I first discussed this idea with Dee and also when I first got the invitation to speak here, I was thinking, like when I first started with generative AI, what's the thing that I think is the most important for me at that time? And I really wish, at that time, I have a very simple guide, something that's clear, something that's practical, that point me to the right direction. So that's the goal for me here today. So I want to give you a blueprint so you can use in your own research. So you don't need to, rebuild the wheel. You can start using what's out there already and do it, in just, under an hour instead of using a couple of days, to get the basic stuff out. And so that you can actually spend more time on the interesting and meaningful part of your own work. Okay, so that being said, let me dive a little bit deeper into the blueprint idea. So first thing is, let's start with the big picture. Let's zoom out. So the core of this whole AI revolution really comes down to two big things, right? The first thing is knowledge, ingesting knowledge, understanding information. And the second thing on the right-hand side is basically making decisions. Like we have the information, how AI can use this information to do this kind of work for us, to make decisions, to actually improve the system, based on this information. So the ingestion loop, this is pretty simple. This is where we take all the data, maybe an organization have, a university have, for example, like documents, PDF, databases, conversations, everything, and we embed it, extract out the important pieces and parts and make it searchable. This is how we turn raw information into usable knowledge, right? And then on the right-hand side, once the knowledge is stored, the AI can actually use it. It can search, retrieve, re-rank, and plan. This is the decision-making loop. So one really good example of this, to combining this two loop, is Cursor. I don't know how many of you use Cursor every day, but inside NVIDIA, all of us have access to Cursor, and all of us use it extensively. For me, I basically spin up 3 cursor terminals, side by side, and let it write code for me. So cursor is a really good example. You basically give cursor the access to your code base. It has the information, it retrieves it, stores the chunk into the database, and then when you ask a question, it's gonna do decisions based on the information that the AI already has, and then it's gonna solve the bugs in your code, apply the patches to your code, and then do another round of iteration. So this becomes a loop. You give it more information, it's gonna make decisions, and it's gonna generate more information and save it back to your database. So we have this what we call internally data flywheel spinning up. So all in all, the idea is simple. Process the data, store the knowledge, let the AI retrieve and act on it, and if you can get these 2 loops right, you can basically connect AI agents to all kinds of data and unlock all kinds of new possibilities. Okay. So with the big idea out of the picture, let's talk about concretely, like what we need to use to build blueprints. So the foundation of everything is what we call NVIDIA NIM. Think about the way that you want to spin up an AI on a local instance. Sometimes it's pretty hard, right? You need to download the model from Hugging Face, convert it into a checkpoint, and then load it up to do inference, to wrap it into a microservice, expose the URL, and then use your own service to call this URL. Sometimes it's really complicated to do all of this, and that's the reason many people turn to, say, OpenAI Cloud to use their own API. But many times, you can't do that because sometimes you're using your own information. You don't want to leak it to other companies, and also sometimes it's a little bit expensive to use those APIs. If you have like multi-billion tokens, you wanna actually process. It takes a lot of money, to get it done in a cloud API. So at this time, you will probably want something that can run locally, something that's easy to use, something you can, pull it down and you can start right away. And this is exactly what we build NVIDIA NIMs for. NIM stands for NVIDIA Inference Microservice. It's basically a Docker. It's in a Docker format, and we basically put everything inside this Docker already for you to use. It will expose the API just like the OpenAI API. It's basically exactly the same. You can use the OpenAI Python packages to call this URI and get the information back. And we support all kinds of open models. We partner with almost every open model company out there, whether it's Llama, whether it's DeepSeek or Q1, any open model, we try to have day 0 support for all these models. And also what's good about that is these models are already optimized by our engineer, so the performance out of the package is already great, already the best on the GPU, so you can start using this right away. So with that, you can with NVIDIA Inference Microservice, we have a AI model as a core for all the blueprints we can build. So this is the foundation layer for all of the blueprints we're going to talk about. And this is super easy to use as well. Basically, you put on Docker and that's it. You can spin it up. Okay, now we have the AI model. The next thing will be the blueprints. The blueprints, we have a lot of blueprints. I'm not joking here. So blueprints is one of the focus we have for this past year, and we have a lot of blueprints available on build.media.com. So if you want to go check it out, that's the website. These blueprints are all open source. The only thing that's not open source is what's inside the NIM container. But if you're just gonna use the container, you don't need to worry about that. So all of these codes are on GitHub. If you want to use it today, go on the GitHub, find NVIDIA Blueprints, pull it out, and you have it. So we have made different blueprints for a lot of different areas of use. For example, digital human for customer services, traditional RAG. RAG is basically the golden standard for AI agents right now, right? And basically retrieve information, save information, and give out answer user questions. So this is basically the foundation of everything. And also the drug screening. We have a lot of blueprints for healthcare industry. And also some for the HPC field as well. If you go to the bottom right, you can see the digital twin for interactive fluid simulation. And this is pretty cool because it basically maps a car inside the virtual space, and you can take whatever car you want, whether it's a McLaren or no, well, whatever car you want, and you can put it into the virtual space and then do simulation on top of that. It's pretty cool. So that's the high-level picture of our name container blueprints. And for next, I'm going to dive into several of the blueprints, going to the architecture, and and we can discuss which component that actually helps for your own research. So first thing, of course, we're going to start with RAG. RAG is basically the most widely used agents out there. This is it's almost used by all of our customer. And every time when I talk to a customer, the first thing I'm gonna say is, do you guys use RAG now? If you are using, we can help you to accelerate many parts of the pipeline, because we have these blueprints right here. So the RAG pipeline is basically two parts, right? The ingestion part and the retrieval part. The ingestion part, we have many different names for each component of a PDF. For example, we have the chart. Well, we can use chart as an image, and we have several different names to extract the information from a chart. And we have the table as an image, and we have a dedicated name for just table extraction. And we can combine the text as well, all of this together, doing post-processing, and use the embedding name to save it as an embedding and save it into the vector database. And when it goes to the retrieval pipeline, when a user actually asks a question, it's going to go to the similar things. It's going to go through the embedding name, and it's going to go into the vector database, use similarity search to find the most relevant answer, do a retrieval re-ranking to re-rank the result and get the most relevant one, and then send to large language model for it to generate the answer and pass it back to the user. So many components here can be used for your own research. For example, embedding. I think the newest model we have ranked the first on the embedding leaderboard. So this is, if there's something that you want to use in your own work, you can put it down and use it right away. Also for chart and also table extractions, these are all pretty good. And if you want to use that, you can use that as well. So that's the RAG pipeline, which is mostly the base for blueprints. And on top of that, we can take bits and parts from the RAG pipeline, and we can create some other use case, specifically for other type of use. For example, the first one is AI virtual assistant. I don't know if you can say this clearly, but basically the ingestion part is almost the same. Just on top of what we already have in the RAG pipeline, we actually have a SQL database, which is structured data. Many times company data or traditional data is all stored in the SQL database, so we want a way to actually extract out that information as well. So that's why we have unstructured data storage and structured data storage, both used as the data source. And then we use this ingestion pipeline to get the information out, send it to the agent gonna do planning, and then use large language model to actually get the information out. And this, the backbone here is similar to RAG, but once you rearrange it, you use it for a specific use case, you actually create a new agent that can solve a lot of things. So that's actually my goal for this talk here. You can see through different component from different blueprints, and then put it together for your own research, for your own agent building. The first one is AI virtual assistant, and the next one I have is digital human. And this is really interesting, is because the previous two, we were all looking at text-based, right? It's chart, it's table, but it's all text-based. It's all on the paper. But what if we want to add a voice capability, or we want to do a visual simulation, like generate a face, generate a virtual human to actually talk to you? So this is what this digital human is for. So when a user actually go talk to this agent, they can do both video and audio. And then the video pipeline is gonna go through our ACE agent, and it's gonna and we're gonna extract out the voice out, and then use it to generate text, and use the text to do all this kind of what we've seen previously, AI virtual assistant. And once the result comes back, we actually use a TTS model to generate a voice based on the result and put it back for user to communicate with the user. And the video part is interesting. Once we have the audio out, we are actually passing to this model right here called the audio to face model. This is gonna in the real time generate a 3D facial expression and then map to the base face, so that you can actually see that this virtual person is actually talking to you in real time. And this also use a lot of GPU rendering. That's basically what we're really good at, from all the gaming stuff. So we use a lot of this rendering stuff as well to combine everything together and stream it back to the user. What's cool about this is that, even though all these models are really huge, we can cut the latency down to a very minimum to make it real time, so that it feels like you're actually talking to this virtual or digital human person, living in your machine. So this is pretty cool. But in this blueprints, it basically give you the tool to actually use voice-based and also this audio to video, like visual-based pipeline, so that you can use in your own research as well. Okay, now we talk about the general stuff, like virtual assistant, digital human, but we can also use all this for specific industry. One example I have here is drug discovery. So there are a lot of new models come out in the healthcare life science industry. For example, AlphaFold 2. When AlphaFold 2 comes out, it's just basically revolutionized the drug industry. Like when you're trying to build a new drug, it used to be you need to go come up with ideas, go into wet lab, and then spend a couple $1 million, try to make this work. If it doesn't work, this couple $1 million is wasted. Now with AlphaFold 2, we can actually do simulation and to make sure that this drug that you're trying to produce have a very high success rate already before going to wet lab. And on top of that, when we have the protein folding, all this, we can actually have a deep dock model to see if it bounds to the molecule, so that further increase the accuracy. So this blueprints basically combine everything together. So for the user can use this as an assistant for doing drug discovery. All of these green ones are also in NIM format. You can pull this down and use it right away. So if you are a research scientist in the healthcare industry, you might want to take a look at these blueprints. We have also vulnerability analysis for like container security. This is especially useful for cyber security space. So if you're in this space and you want to analyze what kind of vulnerability your product has, your container has, this is the blueprint you can go. I'm not going to go deep into that one because I'm not an expert in cybersecurity areas. I'm just going to move forward. Okay, and this one is also a very interesting one. This is called video search and summarization. This is especially important is because we talk about like how to generate how to use text-based information, right? We talk about how to use voice-based information, but when it comes to video, how you gonna actually analyze the video is really interesting. So the key aspect here is vision language model. Traditional large language model nowadays it's not just the large language model itself based on text is not enough nowadays. We need to get all kinds of visual information in there as well. That's why when you use ChatGPT nowadays, they support visual information right away. So this is super important, and when this blueprint actually tells you how to build this kind of pipeline using visual information. So basically, when a video comes in, we're gonna use FMPAG to slice this video, get the key frames out, and then send the key frames inside the visual language model for it to understand and give out insight. And this is pretty cool because since we have a video, we have a time series information so that we can predict once this happens, the next thing gonna happen. Like if we have a video input from a cross section on a highway, if there's a crash, we can predict which next car gonna crash, what's gonna happen in like a couple seconds from now. So this is something that's super useful for if you're doing visual-based research. So basically, with that, we have completed the 3 modality, which is text, voice, and video. Okay, so I'm just gonna. So we talk about all the new things like visual-based large language model, all that kind of stuff. But what happens to the traditional high-performance computing that is still used by many different things, right? So this next couple slides, I'm going to talk about the traditional simulation for the high-performance computing and also for the physical world. Physical world is really the hot topic right now. If you heard 50D and I think Yang Kun, they are all trying to create a company that do physical simulation of the real world, right? And this is our internal work that that start some baby steps toward that goal. We basically use computer-aided engineering to do digital twins for physical objects in the virtual space, and then try to do all kinds of simulation on this. One of the interesting things here, as we talk about, we can do car fluid simulation. This is super useful for a new car for a new car to come out from the car manufacturer. The next one we have here is the real-time sensor simulation for autonomous vehicle development. So that you don't need to drive the autonomous car, on the road for a couple thousand hours. You can basically do simulation, in the virtual world. This is super useful for example, you cannot drive the autonomous vehicle on the road yet, but you want to get more information from there. So this is super useful. Okay, so that concludes all my architecture parts. So basically, we have many different blueprints for different industry, and all of this is available on buildonmedia.com. So if you go on there, you can actually try it out. Register, and it's gonna give you a 90-day free trial license for pull down all the names and all that kind of stuff. And if you like it, you can actually talk to us. We can give you a full access and all that kind of stuff. But yeah, this is all online on buildonmedia.com. So go check it out if you have time. We also have live demo on there as well. So if you you don't want to deploy it right away, you just want to try it out on the website, you can do that as well. Okay, I'm gonna stop sharing. Any questions?
Okay. Oh, any questions from the audience? So if no question from the audience for now, I'm gonna ask a few questions. So I saw you're trying to, show a few examples. I saw like the human simulation, autonomous vehicle, also like the video generation. I guess these are more virtual based simulation, right? So is there any like simulators that are for example, the robotics, which is more materialized? You can sort of see the behavior of the robotics if you add in certain optimizations, right?
Yeah, we do. We definitely have a lot of robotic simulators. So one of the things that we start is Isaac. Isaac is a framework that we built specifically for robotic simulation, and we have a lot of open source model on there as well. So one goal inside NVIDIA is we are trying to make human droid more like human. So this is our ultimate goal. So I think recently we have many breakthroughs, and all of this are achieved mostly, using Isaac. We don't want, because human droid nowadays is pretty expensive, and if it doesn't work, it's gonna fall down. It's gonna break. With like 10K of dollars, right away with just one robot fall down. But if we want to do this in the Isaac in the simulation part, we can render like 10,000 robots, like just doing reinforcement learning in a virtual space. This is actually one of the demos we have inside NVIDIA. We see 10,000s of virtual robots just trying to learn to climb stairs. You can see a lot of robots just fall down the stairs and fall onto the ground. It's pretty impressive to see how many robots just fall down. But with all this 10,000 reinforcement learning robots, we're gonna do multiple rounds, and then finally gonna have a policy that this robot can actually learn how to climb stairs. So I mean, in real world, it's gonna cost a lot of money, $2 million. In virtual world, it's just a couple bucks. That's it. So yeah, we do have a lot of this. So if you guys are interested in robotics, check out Agentic. Talk to our robotics solution architects. They're gonna point you to the right direction.
Okay, yeah, that's very interesting. And definitely, I think the humanoid is something that, for example, Elon Musk is also trying to do, right? But from that regards, I think, let's say you have the human simulator and then you have the robotic simulator. Is there any effort, try to combine these two and make, like you said, make the humanoid more human, right?
Oh yeah. We have a lot of this. So make the human part more human. There's too many different there are many different approaches to do this, and the most important thing is to make the learning uh, from as many situations and many different platform as possible. Like for example, when a human droid is doing like cutting a celery or something like that, it's doing a cut on cardboard many times, if we see that in real world the robot doesn't perform well, it's because he haven't learned what kind of cardboard is doing, what kind of knife is using. But in the virtual world, we actually have a experiment to just swap out different materials, like a wood board was sliding into a stone board, this different kind of things. We use this kind of simulation to make the robot learn as much as possible. So yeah, it's all possible in the virtual world as well for this kind of simulation as well.
I see.
Yeah.
Yeah, that's very interesting.
Yeah.
So any questions for the audience? Okay, if no more questions, probably that's the end of the semester. Yeah, let's thank the speakers once more. Oh, I think Rishi drops. Okay. Yeah, so that should be that. This concludes the semester, all the talks we have. And thanks again, Yang, for giving us a wonderful talk. And hopefully, we can have you back at some point in the future for another different talk.
Yeah, definitely. Looking forward to it.
Okay, thank you so much.
Thank you.
Yeah, enjoy the final, everyone. See you.
See you guys. Bye.
Bye.